Okay. Hello, and welcome to the part 4, and this should be the last part of the neural networks and clustering series. My name is Che. I'm from Northeastern University, and today we're going to go over this deep subspace clustering net by G and Itao. I don't remember if it was published, but it's definitely from 2017. So, yeah, today we're going to talk about this paper here. So, I'm not sure if it was published, but yeah, I probably should have checked that ahead of time. Anyways, so in this one, they still use autoencoders. So based on the name, they essentially just combine autoencoders and sparse subspace clustering together. So, like last one, where we did spectral clustering, if you know sparse subspace clustering, I think you'll be able to guess what they did. So today we're going to go over actually sparse subspace clustering. Okay, so what is sparse subspace clustering? Well, it's based on the assumption that data in different clusters are in different subspaces. So like if we look at this, we have three, like they're all perpendicular to each other, three subspaces, and they live in some kind of plane, right? So we have three clusters, green, red, and blue, and they all live in a completely different plane. And they live, not only do they live in the plane, for this example, they're perpendicular and orthogonal to each other. So we'll let the green, right, data set be x1, 2, 3, and on. So that's, for the green data sets, we're just going to call them x1, 2, 3. For the red data sets, I'm going to call them y1, 2, 3, 4, 5. It keeps going. And for the blue, I'm going to call them z. Okay, just to make it easier to separate the three out in terms of variable, I'm going to name them slightly differently. So at this point, if we pick a point here, right, we'll call it xi from green. And we want to essentially recreate xi using y, so the red dots. Well, it would be impossible, right? If we try to find some kind of combination of adding up the y's, all the red dots, it's easy to see this graphically why it doesn't work. Because no matter, like let's pick this dot and this dot, no matter how you add them together, it's still going to stay on the red plane, right? It's never going to jump out and go on the green plane. So it's just not really possible, like not possible. Now the linear combination of y will, like I said, will always stay on the red plane. So the only way that a data could be represented is really on its own, same subspace. So x, the list of x's can represent this. And the set of y's can represent this. So you can kind of picture, like in the red, some combination of red can form another point here, right? And similarly with z as well. So with x, y, and z, it seems to me that the things, each point can only be reconstructed by other points on the same plane. Same plane. And this property is called self-expression. You can express yourself, I guess, through yourself. Well, that doesn't make sense. Anyway, so even though we do it this way, there's this trivial solution. So for example, the trivial solution is, right here is x, right? If we just put 0, 0, so they're gone. And essentially we're saying x2 is equal to x2. And that's a trivial solution. And we want to avoid that. So what we do is, for xi, we want to make sure that one is 0. And then distribute the weights of how to rebuild it on all the other points. Now, let's stack all the data together. So remember, we had all the x's, all the y's, all the z's. And we'll stack the coefficients together as well. Of course, if we're looking at xi, we don't really know. This is the variable. We don't know what this is. But if we were to know it, and we can imagine what it might be like, it would be something like this, where we're trying to recreate xi, right? And therefore, for y and z, they should all be 0. This is where the weights are. And of course, I can rewrite this in the matrix form. So this right here are the x weights, and these are the y and the z weights. The data in x should be larger. Of course, they are 0 if they're perfectly perpendicular. But if they're, for example, have noise, then they're not exactly 0, right? So as I can see, with noise, they won't be exactly 0, but it'll be small. But for the most part, it's that these weights are going to be much larger because they have the ability to recreate xi. Now this is interesting. Why are we doing any of these? Like, why do we care to find this? Right? Well, think about it. These weights here, right, 0, 0, 0, tells us how related each vector is to xi. So y1, because it's 0, it tells us that it's not related to this at all. y2, similarly, it got a 0. So it's not related to this. None of these are really related. As a matter of fact, these ones are related. So as a matter of fact, the larger it is, like this one is probably very similar to this. So the larger it is, it has better relationship, right? So like I said, this one, -1, is much larger than everything else. So that's a high relationship. Whereas 0 is a low relationship. And of course, we don't care if it's positive or negative. When you have a heavy weight, doesn't matter if it's positive or negative, it's going to be something that's heavy, that's has a high weight. And therefore, this tells you that x3 and xi, whatever xi is has a very high relationship. And then I'm going to use this other notation, right? Before is x times this whole big matrix, I mean vector. I'm just going to call it vi. Okay? So remember, this is vi. This is xi. Okay, so right here, yeah. So instead of only for looking for xi, let's look for x1, x. Let's them. 1 help us find x2, help us find x2, and so on and so forth. Right? X here. See, now we're looking for the whole matrix. This is x. This goes here. And this whole matrix, I'm going to call it V. Instead of V1, V2, Vn, it'll be just V. And once we have this V here, remember what we talked about. V, each element inside here, like Vij, is the similarity between Xi and Xj. Does that remind you of anything from our last video? Similarity, some kind of matrix that tells you similarity. Well, if you remember from last video, we were talking about similarity matrix from spectral clustering. And here's the framework, right? We have some data, and then we get this similarity matrix. But of course, we use the Gaussian kernel, or also known as RPK. And then we found this degree matrix. We did the L, and then we did the V. So instead of using this Gaussian kernel, we can actually use this subspace clustering, right? By finding this vector v, which is the similarity between xi and xj, and replace it here. Right? And that's why it's interesting to find this. This is another way of measuring similarity. And it's based on if they exist in different subspaces. So, like I said, it was previously calculated with this kernel. But in subspace clustering, what we do is we find this V, and that will replace this kernel. Right? So, like I said, this part, last time it was this part that was changed and advised. And this time it's this part that's going to be changed. Well, so how do we solve this? So this is the situation. Now, we don't want to solve V, just any V. We want some special V. We want a V that is sparse, which means there are a lot of zeros inside it. Reasoning for that is, if we look at just xi and vi, which looks like this, right? We want to concentrate all the weights, all the mass in the most important weight, in the most important vectors. And we want everything else to be zero because we don't want to bother with them. So we want this vector to be very sparse. And this could be done with this thing called L1 regularizer. I don't know if I did L1 regularizer in my other videos. But the idea is if you add this L1 regularizer, it essentially makes these vectors sparse. So what we want to do is we want a situation V that satisfies this, and we want to minimize the L1 for the first vector, second, third, fourth, and so on and so forth. For every single one of them, we want to minimize the L1. So this is the second condition. But there's just a lot of these, so it's kind of complicated. Instead of minimizing each one of them separately, we could actually just minimize the max of them. Think about it. If you make the maximum of any one of these as small as possible, you are essentially minimizing all of them. Because if the maximum is small, all of them have to be small, right? And by definition, we can rewrite it this way. So this is the L1 norm for the matrix. So it's no longer V1, V2. This is the whole matrix. If you look at the definition, what we're doing is, so we're summing up all the i's. So we're summing up all the i's, max out of all of them, which is essentially what we're doing here. So this is just a more compact way to write the same thing. So now we have two conditions. First, we want this like self-expression. I think that was what it was called, self-expression, expressiveness. And then we want to minimize the L1 norm. Now there's one more condition, which we actually already mentioned, is that we want to avoid trivial solution. Trivial. What I mean by that is, if we have x3, we could just cancel the two of them, and we get x3 equals x3, and that's a trivial solution. We want to avoid this situation. So to avoid this situation, what we do is, if it's x1, we want to force this no matter what to be 0. If it's x2, we want to force this one to be 0, right? Altogether, if we are looking at every single one of them, notice we are trying to enforce the diagonal to be all 0. So the last condition is, this is V here, right? We want the diagonal of the V matrix to be 0. Okay? So now we have all three conditions. The self-expressiveness, minimization of the norm, and we want the diagonal to equal to 0. Okay, and now we have the cost function. The cost function is that we're trying to minimize the L1, like I said, minimize this, and subject it to x is equal to x times v. Diagonal has to be equal to 0. And this right here is the sparse subspace clustering that we're talking about. And now, well, now that you understand sparse subspace clustering, take a second and see if you can guess how this was later on included with autoencoders, right? Just take a second, look at it. How is this? How can we combine this with autoencoders? So, autoencoders. Now remember, autoencoders, we have the input and output. We want the input and the output to be the same. And over here is the compressed version. So, this right here is the cost function for autoencoders. We want the input and the output to be the same, right? And this one here is the sparse subspace cluster. We're trying to minimize this norm, L1 norm, subjected to these constraints. So together, what we do is we're trying to minimize here's the portion of the autoencoder, and this is the portion of the L1 norm. So we're trying to minimize them simultaneously. Subjected, remember we had x, right here we had x times v. Instead of x, we're going to use the output. Well, not the output, but the bottleneck of the autoencoders. And we want the bottleneck, right, to help us find the v. And of course, lastly, we want the diagonal. So that's basically it. And this right here can be solved. I think you can still use stochastic gradient descent to solve it. I haven't solved it personally, but it looks like we could do that. So in terms of deep learning and clustering, the pattern is pretty simple and obvious. I mean, we've gone through 3 so far, and those are the 3s that's being published recently. And this kind of gives us an idea how to publish a new paper, right? We just pick a clustering algorithm, add autoencoders, and then publish the paper. That seems to be the pattern. But yeah, well, I think that's it. We have gone through the concept of neural networks and clustering, and yeah, I hope this will make you reading the paper a lot easier. I will see you in my next series, I guess. All right, bye-bye.